We're going to calculate and determine the amount of heat in a physical change using Q equals mc delta T or Q equals m times delta H. So do you think it takes more heat to melt water or to boil water, or the same amount of heat? So as it turns out, the heat of fusion is the amount of heat needed to make a phase change between solid and liquid, or melting and freezing. And for water, the heat of fusion is 334 joules per gram. The heat of vaporization is the amount of heat you need to make the phase change between liquid and gas for a given substance, so boiling or condensing. And for water, the heat of vaporization is 2260 joules per gram. So if you have solid ice, it's going to take less energy to melt it than if you had liquid water and you want to try to boil it and turn it into a gas. It takes much more energy to do that. So here's our graph, and the slope lines here, here, and here is where we have a solid, a liquid, and a gas, and as you add heat to them, the temperature rises, right? And so in those three locations, we're going to use the Q equals mc delta T. Where you have the flat line, here is where it's changing between solid and liquid, and so that's going to be the heat of fusion that we'll use to calculate that. And then up here is where it changes from liquid to gas, or in the reverse, and we use the heat of vaporization for this calculation up here. So there are two types of heat calculations. No phase change means on the slope, and you're going to use Q, which stands for heat, equals M, which is mass, times Cp, which is the specific heat of your substance, times the delta T, which is the change in the temperature. Delta T is calculated by taking the final temperature minus the initial temperature. So when you see keywords like raise or lower the temperature, you're going to have to use this equation here. If we have a phase change on the flat line of the graph, we're going to use Q, which is heat, equals M, which is mass, times delta H, and it's going to depend, is it fusion, which is melting and freezing, or is it vaporization, which is boiling and condensing? If given mass, we're gonna only be given mass in our problems. Here's the heating curve of water. So here's point 1, 2, 3, 4, 5, and here I've labeled for you which equation you'll use at which point. So at point 1, because the temperature is rising, we're going to use Q equals mass times the specific heat as a solid times the change in temperature. At point 2, the flat line part, we're going to use Q equals M times delta H of fusion. At point 3, this slope here, we're going to use Q equals mass times the specific heat of the liquid times the change in temperature. At point 4, this flat line here, we're going to use Q is equal to mass times delta H of vaporization. And then at point 5, where the temperature is rising again, we'll use Q equals M times the specific heat of a gas times the change in temperature. So let's do some sample problems. So here's our first sample problem. And the first issue we have is we have to determine which equation are we going to use. Q equals MCAT, MC delta T, or will it be Q equals the mass times the delta H? So to figure this out, we're going to read the question. How much heat means we want to find Q is needed to raise the temperature of 400 grams, this is our mass, and silver from 20 degrees to 65. So this is an initial temperature, this is a final temperature, and since we have this change in temperature, that means that we have a delta T, which means we're using this first equation right here. We also have the value of the specific heat there. Now that we know which equation we're going to use, we're going to plug in our values. We don't know Q, so there's our X, equals the mass is 400.0 grams. The specific heat is 0.24 joules per gram degree Celsius. And then the change in temperature is going to be the final temperature minus the initial temperature. And that's going to be the setup of our problem. We can go ahead and subtract the change in temperature, 65 minus 20, which is going to give us a change of 45 degrees. So now we're just going to multiply it out to solve for X. It'll be 45.0 times 0.24 times 400, and that's going to give us X or Q equals 4,320. Notice the units that my grams cancel, my degrees Celsius cancels, and I'm left with joules. And so this has a unit of joules. Here's sample problem number 2. Which equation are we going to use? Q equals MCAT or Q equals mass times the delta H? So when we read this, it says the temperature of 250.0 grams, there's my mass, at 13 degrees Celsius, that appears to be an initial temperature, is going to absorb this much joules of heat. That's my value for Q. What is the final temperature? So what I don't know is my final temperature, TF. So, and we've been given the specific heat here. So what I have is Q, M, C, and two temperatures, initial and what is the final. So we're going to be using Q equals MCAT because there is a change in temperature. We're not going to use this equation down here. So let's plug in our values. Our Q is 1820 joules equals a mass of 250.0 times the C 0.14, and then times the delta T is going to be the final temperature, which is our X, minus our initial temperature, which is 13. So here's the setup of our problem. So we are going to do our algebra. This is going to be the VU way to do algebra, right? So we're going to always start on the side that has does not have an X. So I want to start here to solve my problem. So I'm going to type in my 1820 in the calculator. So there's my 1820. Now this side has the X right there. So we are going to do the opposite math operation of everything on this side of the equation. So since this is 250 times 0.14, that means I'm going to divide by 250 and I'm going to divide by 0.14. Since this says X minus 13, I'm actually going to add that 13 to solve for X. So we have 1,820, and I'm going to hit divided by 250, divided by 0.14, and then plus 13. And that's going to give me 65 as my final temperature. And so we can actually check this if we want, because if we did final minus initial times this, we should get 1820. So we're going to say 65 minus 13, right? Change in temperature of 52 degrees, times 0.14 times 250, and we do indeed get this 1,820 original amount of heat. Okay, which formula to solve this problem? Ethanol boils at 351.5 degrees Celsius. So we do have a temperature, it's boiling. So that's a phase change, which means there is no change in temperature when we have a phase change. How much heat, so what is Q, that needs to be added to vaporize this mass, 35.7 grams of ethanol? And you'll see that we were provided with a delta H of vaporization here in the parentheses. So we're going to use this equation down here. This is the one you use for phase changes, not this one because we don't have a change in temperature occurring. So now we can plug in our values. We're trying to solve for Q, so there's my X. We have a mass of 35.7 times this delta H of vaporization, which I just put a V here, of 837. Notice that the grams cancel and I'm left with just joules, which will be the unit on my answer. So my final answer is Q equals 35.7 times 837, which is 29,880.9 joules. So that's how much energy it would take to completely boil, change from liquid to gas, this much alcohol. Okay, last example, which formula are we going to use? Here we have the mass of water. It's being melted. That's a phase change. That means there is no change in temperature, no delta T. So that means do not use this equation. We're going to use this one. And it's at its melting point, another clue to use this one here. How many, let's say, joules are required if your delta H of fusion, so here's our delta H of fusion right here, is 333 joules per grams. So now, this is the equation we'll use to clarify we are solving for Q, how much heat, how many joules are required. And now if we plug in our values, Q is what I'm solving for, so that's X. And that equals 31.5 grams times 333 joules per gram. Notice that my grams both cancel with each other and I'm left with joules. So when I get my answer for Q, it's going to be in joules. So we have 31.5 times 333, and that gives us 10489.5 joules of energy.